is our first video on kinetics and reaction rates, and these will be the topics for the next several videos and lesson plans that we'll be covering. Okay, so first for a couple definitions. The speed of a chemical reaction is called its reaction rate. And the reaction rate is a measure of how fast the reaction makes products or uses up reactants. And chemical kinetics is the study of the factors that affect reaction rates, and then also the mechanism by which a reaction proceeds. So exactly how the molecules are combining and colliding with one another in order to cause chemical reactions. Right, so in science and math, we talk about rates a lot, not just reaction rates. And so in general, the rate of some event is measured as the change in some quantity that occurs in a given time interval, right? Or it's the change in that quantity divided by the change in time. So in general, the rate of any process is just the change in something divided by the change in time, right? And so the Greek letter delta we use to mean the change, right? So delta x is going to be the final x minus the initial x. And signs often matter, so it's always important whenever you do a change, whenever you do a delta, it's always final minus initial. And so for reaction rates, we usually define those as the change in concentration of a reactant or product over some time interval. So rather than a generic delta x, right, we're talking about the change in some type of concentration. And so I'm not sure we've used this notation before, but when we put something in brackets, we mean the concentration of that thing. So when I put a chemical formula in brackets, I'm saying the concentration of that thing. So a reaction rate is the change in concentration divided by the change in time. So the easiest way to calculate a reaction rate is to calculate the average rate. So we determine the concentration of A at two different times, right? So the initial time and the final time, and then to get the rate, we just take the difference of those two times. Of course, it's always the final concentration minus the initial concentration, and then the final time minus the initial time. Now, this is considered the average rate because we're really using two different times to calculate the rate, and the reaction rate changes as the reaction proceeds. Very often, reactions get slower as we start to use up the products. So to differentiate calculating an average rate versus a rate at a specific time, if we calculate a rate at a specific time, we call that the instantaneous rate. And if we were to plot the concentration as a function of time, the instantaneous rate would be the slope of a tangent line to the concentration curve, and the average rate would be the slope of the secant line. If you've taken calculus, you can sort of think about the instantaneous rate as being the derivative. And so if we look at a slide here to show sort of the graphical difference between an instantaneous rate and an average rate, this green line represents an average rate, right? We've used this time and this time to calculate the rate of the reaction. To get an instantaneous rate, what we could do is get the tangent line and then just use 2 points on that line to calculate the slope to get the instantaneous rate. Now, in practice, we often use these interchangeably, and especially in this class, going forward, we're not going to make a huge distinction between average rates and instantaneous rates most of the time. And oftentimes, even when we calculate an average rate, we'll just treat it like an instantaneous rate. If you go on to take more chemistry classes, especially after you've had calculus, then the distinction between average rates and instantaneous rates in certain instances might have more significance. One important factor when we think about reaction rates is that the rate of change of reactants and products are not going to be the same, and they're going to be influenced by stoichiometry. And so if we consider this example, so I have nitrogen dioxide decomposing into nitrogen monoxide and oxygen, and due to the stoichiometry, for every 1 mole of oxygen that we make, we're going to make 2 moles of nitrogen monoxide. And so the rate of increase of nitrogen monoxide is going to be faster than the rate of increase of O2. but it's not going to be a random amount faster. It's going to be exactly twice as fast. And so, uh, at least for right now, let's just write down the mole ratios that exist between the reactants and products for this reaction. And so we would say that 2 moles of NO2 will produce 2 moles of NO and 1 mole of O2. So the NO2 and the NO will have similar rates. Now, the NO2 is going to be decreasing and the NO is going to be increasing, but the rate at which the NO2 decreases will be the same as the rate that the NO increases, right? The sign on the rate will just be different. The sign will be negative because we're losing the NO2. It'll be positive because we're making the NO. And then the oxygen will be made half as fast as we're making the NO. All right, so this graph shows exactly what we were talking about on the last slide. So what we've done is we've plotted time on the x-axis, and we've plotted the concentration on the y-axis. And so this green curve represents how the concentration of NO2 changes as a function of time. And as we would expect, because it's a reactant, the concentration decreases. Right? NO is a product, so as we would expect, as the reaction proceeds, the concentration of that product increases. But because of the stoichiometry, the O2 increases exactly half as fast. And so if we were to compare the concentrations of the O2 and the nitrogen monoxide at any point, we would always find that the nitrogen monoxide is twice the concentration of the O2. And you can maybe also tell, right, the concentration profile of the nitrogen monoxide is the exact mirror image of the concentration profile of the NO2. It's just flipped over. And so what we're going to do on the next slide is we want to come up with a mathematical expression for how the rates of the different reactants and products compare to one another. All right, so when we calculate a reaction rate, it should be independent of whatever reactant or product that we use to calculate that. And so we can calculate the rates just like we did before, the change in concentration over the change in time, but we just need to now take into account the stoichiometric coefficients. And so what we want to do is say the rate of the reaction, right, so this is the rate of reaction. We want to say how does that depend on the change in concentration of each of the reactants and products. And so we have to put, right, it's going to be the change in NO2 divided by the change in time, just like we saw before when we're calculating reaction rate. It's the change in concentration over the change in time. And then now to take into account the stoichiometric coefficients, if it's a reactant, we have to put a minus sign in front. So we always want our reaction rates to be positive. Well, if we calculate the change in NO2 divided by the change in time, since the NO2 is decreasing, that's going to give us a negative number. So to make sure that the rate comes out positive, for any reactants, when we write this expression, for the relative rates of reaction, we need to put a minus sign in front. And then to take into account the stoichiometric coefficients, for any reactant or product, we do 1 over the stoichiometric coefficient. So in this case, it would be, for the NO2, it would be 1 over 2. And then we could also write the reaction rate with respect to the products. And it will be equal to what we call the rate of the reaction, as long as we take into account the stoichiometric coefficients. Now for products, because the change of those is going to be positive, the change in time is going to be positive, so we don't put a negative in front. So for reactants, like NO2, we put the negative in front. For products, you don't have to write the plus, but just to sort of drive it home, I'm going to put the plus there. And then I'll do 1 over the stoichiometric coefficient, so it'll be 1/2 times NO, the change in time. And then we could also do the same thing for the oxygen. Only in this case, the stoichiometric coefficient is 1, so it would just be 1 over 1. So typically we wouldn't write that. And so then we have, I forgot my delta here for the NO, so then it would be delta O2 delta T. And so what we've done is we've written the relative rate expression for each of the reactants and products for this reaction. And so I'm kind of repeating myself, but for every reactant product, this is just the change in that reactant or product versus time. So it's delta whatever divided by delta T. And so the only difference is the coefficient we put in front. If it's a reactant, we put a negative. If it's a product, we just leave it alone. You can write the positive if you want, or you can leave the positive off. And then we have to divide by the stoichiometric coefficient. So 1 over 2 for the NO2, and then 1 over 2 again for the NO. Since the coefficient on oxygen is 1, we would have 1 over 1 here, but 1 over 1 is just 1, so I typically wouldn't write that. All right, so let's finish with an example, similar to kind of what we did before. So the first thing we're asked to do is write the relative rate expression for this reaction. And so that's exactly what we did on the last slide. So we just take each of the concentrations of all the reactants and products. For reactants, we have to make a negative 1 in front, and then 1 over the stoichiometric coefficient. So in this case, the rate of the reaction would be minus delta AX4 delta T. For the next reactant, it would be minus 1/2 delta Z2 delta T. For the products, they're going to be positive. So the first one will be positive 1/2 delta X2Z delta T. And I ran out of room, so I'm going to write it down here. And then it would be equal to positive 1 over 1 delta AZ2 delta T. Okay. For the next question here, we want to calculate what is the average rate of reaction between 2 and 8 seconds. Now, having written this relative rate expression, we could calculate the rate of the reaction with respect to any of the reactants or products. However, in this case, they only gave me information about the reactant Z2, so that's the one that I'm going to have to use. So I'm going to say that the rate is equal to, and then I can ignore all these other ones. I don't need them, right? I just need this one. So it's going to be minus 1/2 delta Z2 delta T. And so then we can use the concentrations for the times that we're given. We'll do the concentration at time 2 minus the concentration at time 1 divided by time 2 minus time 1. So what this would look like, I still have my minus 1/2. And then in the numerator, the concentration at time 2, 8 seconds, is 0.0038 minus the concentration at the initial time, 0.0071. And the denominator would be time 2 minus time 1. So it'll be 8.00 minus 2.00. All right, now we could just go ahead and punch all this into our calculator, but I'm going to break it up a little bit just so you can kind of see what's happening. So I've got minus 1/2, and then the numerator I have minus 0.0033, and the denominator I have 6.00. Right, so you can see why we have to have the negative sign for the reactants, because I want my final rate to be positive. So for reactants, when I do the final concentration minus the initial concentration, I'll always get a negative number. And so when I have the negative in front, that will cancel those two out. All right, so then in scientific notation, I'm getting that the rate is equal to 2.75 times 10 to the minus 4. All right, now we need to worry about the units, right? So the minus 1/2 in front, that doesn't have any units, but the units on the change in concentration is going to be molarity minus molarity. So that's going to be molarity. The units on delta T is going to be seconds. And so the units on my reaction rate are going to be molarity per second. or sometimes we'll write that as molarity seconds to the minus 1. Okay, here we have a continuation of the same problem. So I've already written out here the information we determined on the last slide, and now we want to determine what is the rate of consumption of Z2 during this same time period. Right? And so what we're asking is, they're asking what is delta Z2 delta T. And so we know that the rate is equal to minus 1/2 delta Z2 delta T. And so we know the rate, we determined that on the last slide. And so we're solving for this whole thing. So this is essentially like our big complicated X. But just think of this whole thing as X when we want to know the rate of consumption of Z2. And so all I have to do is plug in the rate, move the minus 1/2 to the other side, and that'll give us what we're looking for. Right? So to rearrange that, we just have delta Z2 delta T is now going to be minus 2 times the rate. And so that's going to be minus 2 times 2.75 times 10 to the minus 4 molarity per second. And so we get minus 5.50 times 10 to the minus 4 molarity per second. All right, and then we can do the same thing with AZ2. Right, in this case, rate is going to be just, there's no coefficient in front because it's a product and the coefficient is 1. And so then the rate of the reaction is just delta AZ2 delta T. So there's nothing to rearrange. So the rate of production of AZ2 is all right. And if you want to see another example of this, the next video is just another example of using relative reaction rates.